At the end of the topic, you will be able to define power, explain energy and its various forms, express the practical unit of electrical energy, describe the ways of obtaining energy.
You have seen different automobiles. To understand the concept of power, consider a car and a bike. Car can carry about 5 people and can travel 150 kilometers in an hour, whereas a bike can carry 2 members and go maximum of 90 to 100 kilometers in an hour. Which does more work in 1 hour? Yes, car does more work. Let us see another example. Tom and Tim are building a wall with bricks. Both could accomplish the work. The amount of work done is the same, but the time taken differs. Thus, work done and work done per time are different. The rate of doing work is a measure of power. Power, by definition, is the time rate of doing work. Power can be calculated as work per time. That is, power is equal to work done W by time T. Unit of power in CGS system is erg per second. In MKS system of units, the unit of power is watt. Unit of power is named after the scientist James Watt, the inventor of steam engine. 1 watt of power is the power achieved when 1 joule of work is done, or 1 joule of energy is transferred in a time of 1 second. Power is a scalar quantity.
We know that energy exists in different forms. All forms of energy are associated with motion. Energy is needed to move objects. In other words, the ability to do work is called energy. The word energy is derived from the Greek word energia, which means in action or work. It can be measured by the amount of work done. The commercial unit of electrical energy is kilowatt-hour, kWh, and it is commonly known as unit. 1 kilowatt-hour is the energy used in 1 hour at the rate of 1000 joule per second, or 1 kilowatt. 1 kilowatt-hour is equal to 1 kilowatt into 1 hour is equal to 1000 watts into 3600 seconds is equal to 36 lakh joules is equal to 3.6 into 10 to the power of 6 joules. The energy consumption in industries, commercial establishments and households are expressed in kilowatt-hour.
Whether it be launching of rockets or lifting a book or a falling snow, it is energy at work. Energy has different forms: light, heat, movement, sound, and electricity. Energy always keeps changing form. It can also be stored. A glowing bulb converts electrical energy to light energy. Stove converts fuel into heat, and loudspeaker converts electrical signal to sound. Click each button to know the different forms of energy and their applications. If you stand near the furnace, what do you feel? You feel so hot. Rub your hands together. What do you experience? Yes, it is hot. Heat has the ability to do work. Heat cooks food and produces light. Heat has the power to expand objects, and heat can move objects. The flow of electrons causes electric current. Electrons are driven by electrical potential to move across the conductor. We use electrical energy in different forms. We use electricity to run fan, motor, machinery, lamps, and many more. Electrical generators, batteries, and cells supply electricity. Sun is the source of all forms of energy. Solar energy is used by plants and is used for making and storing food. Solar panel converts solar energy into electrical energy, which is used up in lighting and cooking and in transportation. The heat energy from the sun heats up the sea water, which causes a water cycle, and also nowadays used by the ocean thermal technology in generating electricity. Nature uses solar energy to the fullest. Plants use sunlight in photosynthesis. The man uses it in some devices like solar panels and solar cells to produce electricity. Energy is released during certain chemical process. Food gives us energy by biochemical process, and so we call it biochemical energy. Fuels such as gasoline and petroleum products and food are forms of stored biochemical energy. This chemical energy can be converted into other forms of energy. Enormous energy is released during nuclear reactions. Nuclear fission and nuclear fusion are the two forms of nuclear reactions. Breaking up of heavy nucleus into two or more nuclei is called as nuclear fission. Combining two or more nuclei into single nucleus is called nuclear fusion. Energy released by nuclear fission is used to produce electricity.
We know about the various forms of energy and energy conversions, but where does an object get its energy from? There are actually two ways by which an object gets its energy. The object will get energy when one form of energy gets converted to another form. It can also get energy whenever work is done. Let us try to understand the two ways of obtaining energy in detail. Energy can be obtained through energy conversion. This is based on the law of conservation of energy, which states that energy can neither be created nor destroyed, but it can only be transformed from one form to another. The alternative statement of the law of conservation of energy is that the total amount of energy in an isolated system remains constant but can be transferred from one object to another within the system. Here, system refers to the object of our study. If we take any form of energy, we find that it was obtained from some other form of energy, and that form of energy also from another form, and this gets continued to form an endless chain of transformation of energies. Hence, whenever we say we use energy, it conveys the meaning that we are converting one form of energy to another form. Let us take a few examples to understand this energy conversion. Click on the example button to view the examples. Example 1. In the case of the motion of a car, it is the chemical energy of the fuel when burnt produces heat energy, which in turn gets converted into mechanical energy. Example 2. In the case of windmills, it is the wind energy that gets converted to mechanical energy, which in turn runs a turbine to produce electricity. But heat from the sun causes wind to blow. The source of sun's energy is nuclear fusion reaction. This leads to the chain of transformation of energies. Example 3. In the case of electrical appliances, electrical energy gets converted to light energy, mechanical energy, heat energy, and so on. Example 4. The cooking of food is a chemical reaction which can be transformed into energy inside the human body. When we apply an external force in lifting an object, we say work is done on the object. When we do work on the object, energy is transferred to the object. In other words, there is an increase in the energy of the object. Energy gained by an object is measured in terms of the work done on the object. Let us take an example of a compressed spring. In the compressed state, work is done on the spring, which is stored in the spring as energy. On the other hand, when the spring gets released and comes back to its original position, the same amount of energy is recovered as work in pushing the ball. In this topic, you have learnt power is defined as the rate of doing work. It can also be defined as the work done per unit time. The capacity to do work is called energy. The SI unit of energy is joule. Law of conservation of energy states that energy can neither be created nor destroyed, but it can only be transformed from one form to another.
At the end of the topic, you will be able to define potential energy, list down the various examples of potential energy, explain kinetic energy with examples, derive the expression for kinetic energy, Prove the law of conservation of energy in free fall. Mechanical energy is a form of energy associated with the object's position and motion. When an object gains energy, work is said to be done on the object that leads to the following changes: increase in speed, increase in height or state of strain. Increase in speed leads to kinetic energy, and increase in height or state of strain leads to potential energy. Thus, we can say mechanical energy is the sum of potential energy and kinetic energy of an object. Let us learn about potential and kinetic energy in detail. Potential energy is the energy stored in a body due to its position. It depends on how high the object is from the surface of the earth. A body stores energy when it is held in a position above the earth's surface. The stored potential energy is equal to the amount of work done to raise the object from the earth's surface to a certain height. To lift an object above the earth, we must exert a force equal and opposite to the weight of the object mg. Therefore, work done is equal to force into displacement is equal to weight of the object into height. Potential energy Pe is equal to mg into h. This work done is stored in the object as its potential energy. Let us see some real-life examples that possess potential energy. Compressed spring, raised hammer or axe, stone on top of mountain, drawing a bow, yo-yo held in hand. Stored energy to do work by virtue of its position or state of strain or state of configuration. Potential energy is the energy possessed by a body by virtue of its state. Potential energy due to state of strain is due to the compression or expansion of an elastic object. Potential energy due to the state of configuration is the energy stored within the chemical bonds of an object. Next, we will discuss the kinetic energy. It is the energy of all moving objects. Every moving object possesses the kinetic energy due to its motion. The word kinetic is derived from the Greek word kinesis, means motion. Now, look at this visual. It shows a fast-moving stone shattering a glass. This shows that moving object has the capacity to do work. Using the same examples as potential energy, you can see how the same object that previously had potential energy now has kinetic energy. If the spring we were compressing to give potential energy were allowed to go, it would now have kinetic energy because it is now in motion. Same with the water in the waterfall. When it falls over, it is now in motion. Shooting a rubber band. Water falling. Stretched rubber band. A falling stone. Releasing the arrow from the bow. Yo-yo in motion are the examples of objects that possess kinetic energy.
Let us consider an object of mass m, initial velocity u, final velocity v, and the acceleration produced be a. Therefore, using equation of motion, we get v square is equal to u square plus 2as. On rearranging, it becomes displacement s is equal to v square minus u square divided by 2a. But we know that force F is equal to ma and work done W is equal to F into S. Therefore, work done W is equal to m into A into S. Then W is equal to m into A into V square minus U square divided by 2A. Cancelling A in the above equation, the equation becomes W equals to half m into V square minus U square. Initially, the object is at rest. Then, initial velocity u will be 0. Therefore, work done W is equal to half m into V square. Since the object is in motion, the work done becomes kinetic energy. Therefore, kinetic energy Ke is equal to half m into v square.
When you keep a ball at certain height, due to its position, it gets potential energy. There it has potential energy alone. As you drop the ball, it moves with increase in velocity due to gravity. The stored potential energy is transformed to kinetic energy at every point of the fall. At any point during the fall, the total energy is equal to the sum of potential energy and kinetic energy. When it reaches the ground, the entire potential energy is converted into kinetic energy. This proves that energy can neither be created nor be destroyed. One form of energy is converted into the other form. When the ball is at position A, initial velocity is 0. Hence, kinetic energy Ke is equal to half mv square, which is equal to 0. Potential energy Pe is equal to mgh. Total energy is equal to kinetic energy plus potential energy, which is equal to 0 plus mgh, which is equal to mgh. When the object reaches a position B, the distance traveled by the ball is equal to x. From Newton's equation of motion, v square is equal to u square plus 2gx. But initial velocity is 0 and the velocity at that point is v1. Therefore, the equation becomes v1 square is equal to 2gx. And the kinetic energy is equal to Ke equal to half mv square. On substituting the value of v1 squared, we get Ke equal to half m into 2gx, which is equal to mgx. Now, above the ground level, the ball is at a height of h minus x. Therefore, potential energy is equal to mg into h minus x. Now, total energy is equal to mgx plus mg into h minus x, which is equal to mgx plus mgh minus mgx. Total energy is equal to mgh. At once the ball reaches the ground, the velocity is v and total distance travelled by it is h. Thus, v square is equal to u square plus 2gs. V square is equal to 2gh since u is equal to 0 and s is equal to h. Therefore, Ke is equal to half mv square, which is equal to half m into 2gh, which is equal to mgh. On the ground, the potential energy is equal to 0. Total energy is equal to mgh plus 0, which is equal to mgh. From the illustration, we infer that total energy at every point is constant.
In this topic, you have learnt the energy possessed by a body by virtue of its position or due to state of strain is called potential energy. The energy possessed by a body due to its motion is called kinetic energy.